the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who are currently going through row reduction techniques and echelon forms. This is usually saved for the very end of that material, and we're going to discuss in this video an incredibly important theorem. In fact, it's so important that in the textbook I use, it is actually numbered, which means it's kind of a big deal. It is called the existence and uniqueness of solutions theorem. At least that's what I call it because, well, it's all about the existence and uniqueness of solutions to linear systems. Let's read it first, and then we're going to go back through and really dive into the meaning of this theorem and then prove it. So it's broken into two parts, and I tell my students all the time, really mathematics, as you move through it, really boils down to two big questions for most types of mathematical structures: existence and uniqueness. Does there exist a solution? And if so, is that solution unique? Again, does there exist a solution? And if so, is that solution unique? We're going to go ahead and tackle the very first part of this theorem, because like I said, it's broken into two parts here. The first part reads as follows: a linear system is consistent if and only if, and remember, if and only if is called a bijection. It means that if the first part is true, then the second part must be true. And if the second part is true, then the first part must be true. So a linear system is consistent if and only if the rightmost column of the augmented matrix associated with that linear system is not a pivot column. And of course, prior to this video, you should be pretty familiar with pivots and pivot columns for echelon forms or for basically augmented matrices of linear systems. So diving into this a little bit, this is telling us that if we have a consistent linear system, a system that has at least one solution, it could have an infinite number of solutions, that is, or it could only have one. But the fact is, it at least has one solution. If that's true, then what this theorem is stating is the rightmost column of its augmented matrix must not be a pivot column. And we'll talk about the reason why that is true in a little bit, but I just want to get that first part of the bijection stated cleanly. The reverse part of the bijection is stated this way: if the rightmost column of the augmented matrix for a linear system is not a pivot column, then the linear system must be consistent. That's the actual bijection, or the summary of the existence statement. This guy right here, highlighted before you. So that's a nice way to think about it if you're dealing with this theorem. But I have to be honest with you, that's not really the way that I like to work with this existence theorem. I actually kind of work with the contrapositive of this existence theorem more than I deal with the existence part of this existence theorem, or the straightforward part of this existence theorem. Now, I can't remember if I've already said this in my lecture videos because I'm recording this video specifically about 6 months after I've recorded a lot of the other videos, so I can't remember when I introduced this idea of contraposition. However, I'll go ahead and explain it here slightly. I don't want to go into too much detail, but I'll explain it a little bit. Pretty much every theorem you've seen in mathematics is like an if-then statement. And the if part is called the antecedent, and the then part is called the consequent. That's actually not that important for us in this discussion. I just like to say fancy words. So in this case, in the top part of this bijection, we see the if statement is if a linear system is consistent. What we're going to do is call that statement that a linear system is consistent, we're going to call that the letter P. The then part of that statement is that the rightmost column of the augmented matrix associated with that linear system cannot be a pivot column. Thus, this entire blue highlighted piece is our then statement, and I'll call that Q. So this total statement that's been highlighted so far is if P, then Q. And that's what this little notation right here means. P implies Q. However, we know that because we're dealing with a bijection, the argument goes both ways. Notice in the second statement, the if part is actually the then part in our previous statement. And we called that Q in the previous statement, so I'll call it Q here. And the then part, which is the linear system must be consistent, well, that was the if part in our original statement. I'm color coding it so they match up. I hope that makes sense. So really the second statement says, well, if Q is true, then P must be true. Q implies P, but P also implies Q, so altogether we would say it this way. P is true if and only if Q is true. That's a terrible bijection symbol, so I'm going to go ahead and try it again. There we go. Now to teach you about contraposition, if I haven't already, which I apologize that I've forgotten, but how contraposition works is it basically gives us two theorems for one. Every if-then statement that we've ever been handed in mathematics is actually two theorems. The first theorem is how it's been stated, if P then Q. But the second truth statement is if not Q, then not P. It turns out that the truth tables for both of these statements are identical. Another way for me to state that very cleanly without you going into like an actual first level abstract proof course is to say, if this statement is true, then this statement also has to be true. A clean way to understand it is pretend as though, and I always use this example, so if I've already used it in a previous video, forgive me, I'm using it again. If we let P stand for that it's raining and Q stand for it's cloudy, then that if P then Q statement that we have there is saying, well, if it's raining, then it must be cloudy. Well, let's look at the contrapositive statement. The contrapositive statement is if Q is not true, then P cannot be true. Well, let's see if that's true. What's the opposite of being cloudy? Well, that's not being cloudy. And what's the opposite of it's raining? Well, that would be the fact that it's not raining. Okay, so before I kind of put the nail in the coffin for this contrapositive discussion, let me go back here and say, we all kind of have to agree that, well, first of all, we have to agree that I don't know how to spell. And second, we all have to agree that if it's raining, it's got to be cloudy. Okay, so that makes sense. Now, do we also agree that if it's not cloudy, it's probably not going to be raining? The answer is probably yes, that's right. So this is not a proof that contrapositive arguments work, but it is actually a great justification. Proofs by contraposition are incredibly powerful. And so every theorem you've been handed, as long as it's proven and it's been true, has a second theorem with it, a writer theorem, if you will, that is its contrapositive theorem. And you can test it out by looking at any if-then statement that you've seen in mathematics and look at, well, if I negate the then part, will that imply the negation of the if part? And the answer is yes, it will. So what does that have to do with all the work we're doing right now? Well, if you take a look at all these statements here, if I think about the contrapositive statement of this first piece, well, the original claim is if we have a consistent linear system, then the rightmost column of its augmented matrix cannot be a pivot column. Well, the contrapositive of that is, well, if the rightmost column is a pivot column, right, that's the negation of it not being that, then the linear system has to be inconsistent. That is actually a much more powerful statement. If I have the augmented matrix of a linear system and the rightmost column actually is a pivot column, then I immediately know the linear system must be inconsistent. That's a more powerful version of the existence statement. By the way, you could also look at the contrapositive of this piece right here. Just take the negation of this yellow statement, right? The then part. So suppose the linear system is inconsistent, then negate the blue part. That will imply the rightmost column of the augmented matrix is a pivot column. And by the way, that, I'm just going to scroll up a little bit, is more powerful, I think, than the original existence statement, and I have it right here. A linear system is inconsistent if and only if its rightmost column is a pivot column. That's a very, very powerful statement. The second part, which is the uniqueness part of this theorem, is a little more understandable. Suppose that a linear system is consistent, so in other words, that we have a solution, if not more than one solution. Well, if there are no free variables in that system, that is, every column in the coefficient part of the augmented matrix is a pivot column, then the solution must be unique. Otherwise, there are infinitely many solutions. And this gives us a great idea of when we have a unique solution versus when we don't. We have a unique solution to a consistent system if every column is a pivot column in the coefficient part of the augmented matrix. That is, as long as every column in the augmented matrix is a pivot column besides the rightmost column. However, if in the coefficient matrix part, we have a column or two or three or whatever that are not pivot columns, yet we know that the system is consistent, then because those non-pivot columns exist in the coefficient part of the augmented matrix, we have free variables, and therefore we will have infinitely many solutions. What I'm going to do in this video, just to finish it out, is only prove the existence part, just because I think it's important to see that. And the way I'm going to prove this is by contradiction. I think proofs by contradiction are a blast. They're really fun to do, and it's great to see. So I'm going to walk you through the proof by contradiction of the existence part. And usually when you're doing a proof of an existence uniqueness theorem, you're going to do it in pieces like, okay, here's my proof of the existence part, for example. And then if you're going to use contradiction, you tell the world, by the way, I'm doing this proof by contradiction. And you note here that I'm saying which direction I'm going. So I'm telling the world, I'm going to start the proof of this highlighted existence theorem, but specifically I'm going in the forward direction. That is, I'm going to suppose that this is my if statement, and the rest, the back end here, is my then statement, okay? So this is the direction we're going to argue first, and then the second half of our proof will argue the other direction. So for right now, this is our P, and this is our Q. So let's go ahead and give it a whirl and see what happens. Well, what do we need to do if we're going in the forward direction? Well, we need to suppose that we have a consistent linear system. So given a consistent linear system, right? That's what I say right here. We're supposing that we already have a consistent linear system, but we're going to argue by contradiction. And when you argue by contradiction, what you want to do is say, well, I'm going to suppose our if statement is true, but I'm going to suppose that this is not true. I'm going to say, suppose that Q is just not going to be true. And working with that supposition, we should arrive at a point where the world falls apart. Something goes terribly wrong. And the only thing that we will have supposed in the entire proof is that Q is not true. And therefore, that supposition, if the world falls apart, must be wrong, which would mean Q would have to be true. That's how a proof by contradiction works. You'll see it. So let's go ahead and suppose that P is true, but Q is not. So suppose that we've been given a consistent linear system, and also suppose, that's a key word here, we're going to suppose the rightmost column of the augmented matrix is a pivot column. Now, for convenience, we're going to let A be the original augmented matrix of the consistent linear system, and we're going to let B be any echelon form of A. That's just going to be important as we move forward. So we have some original linear system, right? And we go ahead and plug that into an augmented matrix, and then we do some row operations, and we eventually arrive at an echelon form that we're going to call B. Well, if B is an echelon form and the rightmost column of the augmented matrix is a pivot column, there must be a row in B that is full of zeros except for the final element, which would be non-zero. So let me go ahead and say that here. And that's what I have written here. Then there exists a row in B of the form 0, 0, 0, 0, 0, all the way down until we get to some c where c is non-zero. Now, if you think about the equation corresponding to this row of our echelon form B, well, that means that equation will tell us that 0 is equal to some non-zero number c. Since there's no solution to this equation, the system corresponding to B must be inconsistent. Therefore, the system corresponding to A also has to be inconsistent because row operations don't change the underlying solution set. However, this totally contradicts the fact that the system is consistent. We've just arrived at the fact that we have an equation that tells us that 0 is equal to something other than 0. That's a big no-no right there. That's a massive issue. Once we get that equation in our system, we immediately know the system must be inconsistent. However, we were given a consistent linear system. Row operations do not change solution sets, so what the heck happened? We must have made a mistake somewhere in our proof. And that mistake is called a supposition. We made some type of wrong assumption or supposition somewhere. Now, if you read through the proof all the way up to this point, you will see I don't have the word suppose in any of these lines. We did not assume or suppose anything except for this first time. The only time that we supposed something was when we supposed the rightmost column of the augmented matrix is a pivot column. So that supposition must be where our proof broke down. And that's what this statement here is. Hence the supposition that the rightmost column, this part right here, of the augmented matrix is a pivot column, that must be false. And thus, the rightmost column of the augmented matrix for this linear system cannot be a pivot column. Again, our only supposition was the rightmost column of the augmented matrix was a pivot column, and that actually caused the world to fall apart because we started with a system we knew had a solution, and we got to a point where we couldn't have a solution. So our supposition was wrong, and therefore it's a contradiction, and therefore we know the opposite of our supposition must be true. The rightmost column of the augmented matrix for this linear system cannot be a pivot column. Now, before somebody stands up and says, hey, just because one thing's false doesn't mean the other's always true, that is a true statement if you had 3 or more options. But when you only have 2 options, on or off, true or false, well, if one doesn't work, the other one has to. That's just how it is. So that is the proof that if we have a consistent linear system, then the rightmost column of the augmented matrix cannot be a pivot column. Now we're going to go the other direction. We're going to go ahead and prove backwards. And we're going to do it the same way, by contradiction. So again, remember, the last statement is the Q part, the first statement is the P part. We're going to go ahead and prove it this way. If Q, then P is what we want to do. But again, we're doing it by contradiction. So we're going to go ahead and say, assume Q is true and suppose P is not. We're going to arrive at a contradiction. So we're going to state that the rightmost column of the augmented matrix is not a pivot column, but we're going to assume or suppose that the linear system must be inconsistent, which is not true actually, but let's go ahead and try it out. So given that the rightmost column of the augmented matrix for a linear system is not a pivot column, suppose the underlying linear system is inconsistent. Well, what does that mean? We happen to know an inconsistent linear system has no solution, and so we must have an equation in our linear system of the form 0 is equal to c, where c is non-zero, and this is only true really after row reduction. Thus, the augmented matrix for this linear system must have a row of the form 0, 0, c, where c is non-zero. Thus, the rightmost column of the augmented matrix for the linear system is a pivot column. However, remember, we're stating given the rightmost column of the augmented matrix for a linear system is not a pivot column, then we're going to suppose the underlying linear system is inconsistent. With that supposition, we arrive at the fact that the rightmost column must be a pivot column. Well, that's contradicting our very first highlighted statement right there. It's a total contradiction. Thus, the supposition that the linear system is inconsistent must be false. Well, what's the opposite of a linear system being inconsistent? It's that the linear system must be consistent. And we have proven that if the rightmost column of the augmented matrix is not a pivot column, then the linear system must be consistent. And that is the whole proof, QED, the whole proof of the existence part of the existence and uniqueness of solutions theorem. Now, I would not imagine that a student who's right at the beginning of the linear algebra would be able to regurgitate this. However, you should be able to follow the logic, and there's a lot of important things going on in the background that I want you to really spend time really wrapping your minds around. For example, you should really get to know proofs by contradiction, and you should really try to understand what contraposition is. If the statement is if P then Q, its contrapositive statement, which is also true, is if not Q, then not P. That is incredibly powerful as you move forward in mathematics, and specifically in linear algebra. But to end this video, I'll just state this. It's very, very important at this juncture of the course just to know, if you have a pivot in the rightmost column of an augmented matrix for a linear system, that linear system has to be inconsistent. If the rightmost column is not a pivot column, that linear system will be consistent. It'll have one or more solutions. It'll have one solution if all the other columns are pivot columns, and it will have an infinite number of solutions if any of those other columns, other than the rightmost column, does not contain a pivot, or basically they're not pivot columns. That means you have free variables. And once you have free variables in a consistent system, you have an infinite number of solutions. Now that's really hefty stuff to digest, so I will leave it here. I hope you guys have a wonderful day and be good humans.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.